Spain. Our institute is located in Argentina, between the city of Buenos Aires and the city of La Plata, closer to La Plata than to Buenos Aires, but we are close to these cities, so this is why we have many RFIs. But here you can see two pictures where I show you the two antennas that we have at the institute. So our campaign started in 2019. We use both antennas to perform observations at a central frequency of 1.4 GHz with a bandwidth of 56 MHz that we are currently upgrading to 400 MHz. And the advantage of this monitoring is that we are the only users of these radio telescopes, so we use them exclusively. We only use them for pulsar timing. So we perform observations of up to 3.5 hours daily on selected targets. The topics that we study are the detection of and analysis of glitches. We also study millisecond pulsars and the radio emission of giant pulses of magnetars. I will start talking about glitches. As you probably already know, glitches are sudden spin-ups in the rotational frequency of the pulsars. And although their cause is still not well understood, they are probably related to the behavior of matter inside the neutron stars. So glitches allow us to study the behavior of matter at very high densities. They have been observed in 100 pulsars, and some pulsars, for example, the Vela pulsar, show glitches quasi-periodically. For example, the Vela pulsar shows a glitch every 2 or 3 years. When we observe a glitch, we can see as this left, like you can see on this plot, we see a sudden spin-up in the rotational frequency of the pulsar that sometimes is followed by one or many exponential decay terms. This is the behavior of the rotational frequency of the pulsar during a glitch. And when we characterize the glitches, we mainly use this parameter, which is the relative jump on the frequency. If we plot an histogram, as Espinosa did here, of the relative jump in the frequency for many glitches, we will find a bimodal distribution, where the first peak corresponds to what we call the small glitches, because the relative jump of the frequency is of the order of 10 to the minus 9. And the other peak corresponds to giant or common glitches, where the peak is of the order of 10 to the minus 6. This bimodal distribution may suggest that glitches could be triggered by two different mechanisms. Therefore, it is really important to understand the nature of glitches. However, the left part of this plot is not, we are not sure if it is complete, because small glitches are really hard to detect. So it is really important to detect the small glitches to complete this part of the plot. But in order to detect the small glitches, it is really necessary high cadence monitoring. They are hard to detect if the cadence is not really good. Well, when we detect a glitch, we do it mainly by visual inspection. You can see that here we have the residuals, and then at this point, there is a sudden spin-up in the rotational frequency of the pulsar. Therefore, the residuals start to behave with this linear pattern. And later, the residuals will start to show this kind of parabolic pattern, which means that there was also a change in the spin and rate of the pulsar. So by visual inspection in the residuals, we can detect glitches in general, at least giant glitches. And once we detect the glitches, what we do is to plot the frequency and the derivative of the frequency as a function of time. And also we include the glitch in the timing model. As you can see, we include in the timing model a phase change. We include jumps for the permanent jumps for the frequency and the derivatives of the frequencies. And also, sometimes it is also necessary to include one or many recovery terms. As you can see, for example, in this bottom plot, there was clearly a recovery term. So far, in these 4 or 5 years, we have detected 7 glitches, two giant glitches in J07 and J17, but also we detected the 2019 and the 2021 glitch of the Vela pulsar, and also we detected 3 mini glitches, and I mean mini or small glitches in this pulsar because they are of the order of 10 to the minus 9. But I want to point out 2 things. On one side, during the 2021 glitch of the Vera pulsar, the monitoring was already working really good. So we were the first to detect this glitch. Even we detected 2 hours after it happened. And we found a recovery term of 1 day and 1 recovery term of 6 days. And this is only possible if you monitor the pulsar every day. On the other side, we have detected 3 really small glitches in this other pulsar, which again is only possible with the high cadence. Therefore, I will take a moment to point out this advantage of the high cadence monitoring. As I say, one of them is the recovery terms. If we look at this plot, we will see all the decay terms that have been reported for Vela glitches. And if we don't take into account the black dots because they were observed in a glitch that happened during the detection, the next small recovery term detected is the one that we reported, which is this red point here. And it makes sense because it is a recovery term of 1 day. So you will only be able to find this kind of recovery term if you look at the pulsar every day, as we do from Argentina. On the other side, here we have all the glitches that have been reported for J1048. And as you can see, the 2 glitches that we reported are the smallest glitches reported for this pulsar, and we were the only one to detect the glitches, at least by now. And again, this is possible only with the high cadence. And even the new glitch that we are characterizing in this pulsar, it looks like it is even smaller than these 2 glitches. And I want to remind you that this kind of detection are really important to complete this plot that will probably give information on how glitches are triggered or the nature of glitches. And one of our main goals about glitch detection is the live detection of a glitch. This means that we want to detect the glitch, that the glitch happens while we are observing the pulsar. This happens just once in this paper, was reported in this paper of Paul Freeman et al. And they found that there was changes in the magnetosphere during the glitch, as you can see on the right plot. And also they detected 4 recovery terms. This information is really important to the understanding of glitches, and this is why we are working in order to have a live detection. We observe the Vela pulsar almost 4 hours every day with both antennas. So we have 1 possibility in 6 of detecting a live glitch. And the last glitch was in July 2021. And as I say, this pulsar has a glitch every 2 or 3 years. So the next glitch should happen really soon. Now I will move on to one of the other topics, which are the magnetars. When we observe magnetars, what we must do is to look for giant pulses in magnetars. So we have our observations, we integrate in frequency for different values of dispersion measure. So we construct many time series for different values of dispersion measure. As you can see here, we have from the DM0 to DM500, and in this case, the value of the DM for the magnetar that we are observing is 180. Once we have all the time series, we look for pulses with signal to noise greater than 8. And then we have this plot where we have time in this axis and the value of the M here. And we have a dark circle where we detected a giant pulse or a pulse. And as you can see here, we have many dark spots. We have in particular 6 dark spots on this plot, but all of them correspond to a value of DM 180. And as I said before, the DM for this magnetar is 180. Therefore, all of these giant pulses are actually coming from the magnetar. We made a study between September 2022 and May 2023, and in less than a year, we detected more than 200 giant pulses coming from this magnetar, which gives a rate of 1 giant pulse per hour. This is a really high rate, and as you can see here, we observed high activity. Even we observed some giant pulses of signal to noise 40 during January 2023, and then it looks like it turned off. And I want to mention that we are observing this 4 years after the last outburst of this magnetar, which was during 2018. But also point out that some of the giant pulses are really, they really have high signal to noise ratio. So we want to investigate the relationship between giant pulses and effervescence. So on this plot, we have these pink dots, which are the giant pulses detected 1 year after the outburst of the magnetar. These are different FRBs detected, and if we plot our highest giant pulse detected, it is somewhere in the middle between the giant pulses and the FRB. And this happened also for another magnetar before, which is this one with the black points. So this could give us signals about the relation between giant pulses and effervescence. Anyway, this is what we are working on right now, and is still work in progress. Well, I want to also talk about our possible contribution to gravitational wave detections, but people already talked about what a PTA is before, so I will move on to what we are doing. When we started our campaign, we asked ourselves how we could collaborate with detections of gravitational waves with our equipment. So we started to observe the brightest known millisecond pulsar, which is J04. And after 13 months of observations, we collected 366 observations, which means more than 360 hours with each antenna. Then we published a paper where we calculated our sensitivity to gravitational wave detections, and we can see that we are still one order of magnitude away from most favorite scenarios for gravitational wave detections. But I want to point out that the high cadence, the up-to-date cadence, allow us to have sensitivity to gravitational waves, even to a frequency of 10 to the minus 5 hertz. After that paper, we kept collecting observations of this pulsar. Nowadays, we have more than 4 years of fact to daily observations with, you can see the residuals with the first antenna at the left. With the first antenna, we have collected more than 1,400 hours of observation of these pulsars. And with the second antenna, we collected more than 2,000 hours of observation. And we recently found a clock drift, as you can see on the residuals, that we have to find out how to fix. Anyway, all of these data will be analyzed in a future paper that we hope will be published next year. Anyways, we have been only monitoring this millisecond pulsar because our sensitivity is not really good. But as I said, we are currently upgrading to new bandwidth. We are moving from 56 megahertz of bandwidth to 400, and we are performing a short characterization of the new bandwidth currently. And we found that, for example, a typical observations that has signal to noise of 98 now has a signal to noise of 367. And between the improvements, we can see that the shape of the pulse is much better defined now. Same with the plot version measure, which it is much better defined now. And I also want to mention that we expanded our bandwidth in a factor of 8, but we didn't find too many RFIs, which is a good surprise because we are close to civilization, so we expected to find more RFIs. Also, the uncertainties of the TOAs are improving from 0.8 and 0.9 microseconds to 0.3 and 0.1. Anyway, this is still work in progress. We still have to work on the characterization of our new backend. Also, with this new backend, we have more sensitivity, so we plan to extend to our observations to other pulsars. For example, this pulsar, J1909, it is 10 times fainter than the pulsar that we have been observing. But with the new backend, we are capable of observing it, so we have to find out again which pulsar we can observe in order to become our own PTA. Finally, I want to talk about a project that we are developing, which is the multi-purpose interferometric array, also called MIA. MIA is a project that the Argentine Institute of Radio Astronomy is working in, which will be an interferometer that at its first phase will operate between 1 and 2.3 gigahertz and will consist of 16 antennas of 5 meters diameter. The minimum baselines of the interferometer will be 50 meters and the maximum baseline will be 55 kilometers. Anyway, this will not be located at the institute, but will be located somewhere else in Argentina because of RFIs. The final goals of this interferometer is to consist of 64 antennas and operates even to lower frequencies of 0.1 gigahertz. This interferometer will be used for pulsar timing, but will be also used to other kind of research like transient sources, etc. Anyway, we are still not really building this interferometer because first we are working on what we call the MIA Pathfinder, which is a technological demonstrator. This means that we are working on this MIA Pathfinder in order to prove our capabilities to build this interferometer. The MIA Pathfinder will consist of only 3 antennas and they will be located at the institute. As you can see, here is where they will be located, and here we have the other 2 antennas. One of the antennas is already built and we already have the backends, so we hope this interferometer will be finished by 2025. So to summarize my talk, I want to mention that our challenge is both scientific and technological because we are working on data analysis, mostly of pulsar timing, but also we have to develop new equipment to have better observations, and that from Argentina we expect to contribute to gravitational wave detections and also to FRB detection. I want to mention also that we detected 7 glitches in 5 years, but I want to point out the importance of high cadence monitoring in order to the understanding of the nature of glitches, both because of the detection of small glitches and also because of the characterization of short recoveries. On the other side, our high cadence allows us to detect more than 200 in giant pulses in a magnetar in just a few months or less than a year. And this was happening 4 years after the last outburst of this magnetar. And finally, just to remind you that our main goal is the live detection of a glitch, that we hope we can do it for the next glitch of Vela, and that we are planning to observe more pulsars in order to become a PTA, and more magnetars, and we are considering the possibility to detect FRBs too. So that's all I wanted to say. Thank you for listening.
So thank you very much. Ezequiel, are there any questions from the people online? So I think that it's all very interesting and very exciting results, and clearly demonstrate the power of daily timing observations. These are clearly, something that we need both to better model our pulses, but also to detect, to open up this new discovery space. It's kind of complements what Paolo said in the previous talk very well.
Yeah, Paulo also mentioned the importance for phase connection of the residuals, and all we observed 10 pulsars for glitch detection, and we have all the solution in these 4 years phase connected because we observe them almost every day.
I have a question about this. What will be the total aperture of the array if you combine it with if you combine it with the surface as a single dish? They have 16 antennas, maximum baseline, so 5 meters. Yeah, I was just wondering
about 30 meters, 25 meters equivalent.
Sorry, I couldn't hear really well.
I was just so I think the final goal with 64 antennas, you'll have the equivalent of 8 times 5 meters, so about a 40-meter dish. The reason I was asking about that is because it would be really interesting in the future to have some kind of VLBI between Parkes, Meerkat, and your telescope here, because then you have really nice coverage in the southern hemisphere.
Yeah, yeah. Of course, it will be really interesting, and mostly because of our location, there are not many radio telescopes in the southern hemisphere, and I think this will be the first interferometer of this band in Latin America. I mean, with just such lower frequencies. So yeah, it will probably be a really nice collaboration.
Okay, so thank you very much again, Ezequiel. So